Hi. So I've decided suddenly to make different videos, and so in this video mainly we will be kind of moving. So I will come back quickly through the previous two slides related to generative AI, but now I want to give it a separate video because it's mainly connected to previous content we covered in the previous two videos: attention, self-attention, the multi-hit attention. Once understanding all this, we were able to understand and dive into, like, in more details into the Transformers architecture. Then Transformers architectures were mainly the basic building block for language models. And in this context, we went through GPT and BERT to understood the difference between both architectures. And now we are coming back to our context, which is generative AI. So in generative AI, we will discuss three main points related still again in the context of language models. So we will discuss foundation model from this perspective and the evolution of large language models. In addition to LLMs, we are going to discuss them and so on. Okay, so quickly to show you this figure, it shows mainly like where we are standing today. So we are in the context of generative AI, and here transformers are being used. Okay, and the idea of transformers used in generative AI is kind of create a new content, which could be written, it could be like visual, it could be auditory content, and that is mainly going to be based on what we call prompt or existing data. Okay, so this is the idea of generative AI simply. And as I just mentioned, that there are many generative AI tools, and it's kind of a boom that we witness on 2020. Okay, and this boom mainly given birth to transformer based neural networks. We start talking about, in particular, large language models. Okay, so today many of the tools we interact with on our daily basis are based on these language models. Like, for example, the chatbots in general, like we have ChatGPT, Caplot, Gemini, LLM, text to image, artificial image generation. And so for this context, we mainly discuss Stable Diffusion, like Midjourney, DALL-E, text to video. Like these are for text to video, we have Sora and like many other tools. Okay, so today, and there is a huge competition, let me say, in the market today between companies for the development of these tools. Okay, so we are not going to focus for now on image generation. We discussed that a lot in the previous first videos. We will not, what we will focus maybe on is large language videos at least. So let me say, the companies probably developing this kind of products could, like I mentioned, include OpenAI or Microsoft and Google and so on. Okay, and so it's a huge competition being taking place. Okay, so the thing is that the common point is that all of these technologies or tools, they rely on transformer architecture, and that is kind of directly, so we can see that, or somehow, indirectly. Okay, so if we take the example of LLMs, okay, when I say LLMs, it means like ChatGPT or DeepSeek and so on. So these are 100% transformer based. Okay, the idea of 100% transformer based is that, like we've seen in the architecture of these models, GPT model, for example, they are decoder only or encoder decoder variants. Okay, this is the main idea. And so for now, moving from large language models to text to image, and also there is text to video models. Okay, and in these models we can discuss probably Stable Diffusion, the Midjourney, and DALL-E. And for this particular like class, what we can mention here is that like inside of these architectures, there is always a transformer, okay? Whether you can think of it, BERT could be there, otherwise other variants, like for example T5, like text encoder and so on, okay? So without the transformer text like encoder, these models, they cannot understand prompts, okay? So this is why if we are covering transformers in details, it means like we are having, let me say, the key to large language models, because it's like based on that concept, encoder and decoder, only with the minor changes in the architecture, like we discussed last time, okay? So now within the generative AI context, let's discuss this. Now, what happens is that we have the introduction of foundation models. What are foundation models? Mainly, they are large, like, or general purpose models that are pre-trained in a way that it makes them adaptable across multiple tasks. Okay, so we use them in many tasks, and most of foundation models are built as LLMs, like or large self-supervised models, okay? And so these models are trained using two main approaches, whether the supervised learning or the self-supervised learning. So this is important because like obtaining kind of fully labeled or supervised data set at this scale, imagine you are talking about huge data sets, so that is extremely difficult, and sometimes it's even impractical, okay? So instead, like what we do, like, or these models, what they do, so they learn directly from massive amount of raw text, or it depends on the data type also. If audio, then they will learn from the massive amount of audio or images. And the idea is that they are going to learn without like requiring any human annotation, okay? So the key is in what we've seen so far. So what we saw earlier, that pre-training involves like using huge data sets. Sometimes we have trillions of tokens, and like this scale of data combined with deep learning architectures or deep neural architectures, themselves, they contain kind of billions or even trillions of parameters. So this mainly enables foundation model to acquire like broader or let me say generalizable knowledge, okay? So because of this, let me say now, foundation models, they serve as starting point to many specialized applications. And the idea is that we work on fine-tuning them. So by fine-tuning them, we can adapt the same pre-trained model to different downstream tasks, okay, or different domains, or even different modalities. So this is the main idea behind foundation models. And here is the big picture. So now let's take a look on the evolution from machine learning first to then we had deep learning and to today's foundation models. Okay, so in traditional machine learning, the entire workflow like was feature centric. What we mean by feature centric, it means that we focused heavily on the pre-processing. And let me say, the pre-processing was mainly done manually. Like we talk about feature engineering, manual feature engineering, and what we did all the time, it's like selecting the right like transformations before the model, or even like uh, before that the model starts learning. Okay, so next, what happens is with deep learning, this has changed. So we are moving from feature-centric approach to model-centric approach, okay? So here, like the feature extraction with deep learning became part of the model itself. And now, so the idea is that this change make deep learning known as model-centric, because if everything happens within the model. So for almost a decade now, since like let's say from 2010 to 2020, what we have like deep learning dominated. And how it like dominated, it mainly, I would say, took the place or of like typical, I would say, machine learning approaches, and somehow, okay, it's not mainly, but we can say that it's dominated. This is the right word, and mainly this is like the belief changed, and there is no paradigm would outperform deep learning. This is what we all thought, and what we all at a given point, like in 2019, 2020, this is what we all believed. So as someone who did my PhD in deep learning, and I've been working on that from, let's say, 2020 to 2023. At that time, I started during my master in 2007, 2020, working on that. So 19, sorry. So at exactly 2019, 2020, I thought nothing will be deep learning. And during my PhD, I started feeling that there are some challenges related to deep learning, like an explainability, like robustness, like there is these problems which are mainly reason, the main reason behind these is the model-centric approach, okay? Or so what happened now that we the feeling is right. So there is a transition, there is a revolution, I would say, happening. So this is happening mainly with foundation models. So with these models, what happens is that we move to a completely different mindset. So these models are having different, like, I would say, design or structure or idea behind them. And the idea mainly is that these foundation models are data centric. So see the beauty that we are moving from feature centric to model centric, and today we are discussing data centric. And so the power for this foundation model means they come from massive pre-training or extremely large data sets, and their strength mainly lies in their ability to generalize across using generative fine-tuning. Okay, so the way we think about, like, maybe also changes is like, we are no longer handcrafting features, and we are also no longer fine-tuning small models. Instead, like, we rely on large scale, and when I say large scale, I mean it. So we rely on large scale, like pre-trained models developed by major companies. Like, we are using daily products by Google, OpenAI, Meta, DeepSeek, and so on. So each of these is companies mainly is investing heavily in their own foundation models, like, for example, GPT. So now, with the availability of large computational resources, and this was maybe the limitation in 2000, why we don't talk about foundational models, or in 2010, because there was a problem related to resources, okay, to hardware and so on. And this is the first problem. The second problem is related to data sets and the size of the data sets. So today, with the content mainly available, I would say, everywhere, and data is accessible, so there is enormous data sets, and so we have this in hand. So the landscape is shifting again because of these main two reasons. So the future is now increasingly driven by data, by models, data-centric approach. So where models are capable of learning from data, okay, and at its scale, I would say, which is very important. So this is the paradigm that we are entering today, and this is the revolution coming with generative AI. So these tasks, like, for example, like we have the question answering task, sentiment analysis task, information extraction, image captioning, object recognition. So they include working with text or data, okay? It can also work with image data. We can use speech, we can use structural data or 3D signals, okay? So all of these modalities are today possible to be used, and we have data set rich and like huge data sets in these with these different modalities. So after the training phase, once the foundation model is ready, what we do like is we can use it across wide range of let me say downstream tasks. And so now these tasks include like I mentioned, the question answering, these all tasks. So the idea mainly is that we have data, and the data, let's say, is the key. Okay, so the idea is clear, like what we have single foundation model. Once it is trained on massive multimodal data, because here the model is mainly trained on images, trained on text, training on different modalities. So this allows it, or gives it, the ability to be adapted to perform like many different tasks or many applications. Okay, so this is the main idea. And now we have, as I mentioned, different companies. Each of them is having its product. Like, for example, Google has Palm 2, OpenAI has DALL-E for images, GPT-4 for like language, Meta has LLM, and Claude by Anthropic, and so on. So, like, it's a huge competition, and this competition mainly is bringing us to this language model evolution. And now, so let's look to what happened up to 2020, at least. Like, this is the transition, because next is kind of exponential. So up until 2020, so the ability of large language models kept increasing over time. So back to 1990s, what happens, models were extremely limited, like we discussed. They could only assist with very specific tasks. These early large models were mainly statistical models, so they heavily rely on lots of math, formulas, probabilities, and mathematical formulations. Okay, so of course, like, the computational resources were also limited at that time, and they were extremely small. Basically, even like knowledge has been developed using a pen and paper level, like as compared to today. Okay, so next, around 2013, we have the things maybe like improved with neural language models. Okay, so we started having, let me say, better like hardware and maybe more computational power. So language models became able to solve NLP tasks. And this is also when word2vec appeared. Okay, so it's a very like influential idea, just like CNN's revolutionized like vision. Word2vec revolutionized like NLP field, and the idea is that they introduced static word embeddings that could be fed into the neural networks. So it gave us the feeling that deep learning could really transform language understanding. And after that, now in 2018, the concept of pre-trained language models appeared. So this dramatically improved task-solving capabilities. And when we talk about task-solving capabilities, the models that has been used or employed are like BERT. Like for BERT, we were discussing in details in the previous video. It could solve multiple NLP tasks using only the encoder part. Okay, and GPT mainly is used to use mainly the decoder part, and it can also solve like such like capabilities or problems. So these models now are considered pre-trained LLMs. They are powerful but still limited in scope, which means then, like, the idea is that some other move we are taking. So 2020, like the GPT played a key role as a bridge. Okay, so GPT is the model that like we seen last time, it relies like on like the decoder part, okay, of the architecture, of the encoder decoder architecture. And let me say it's like really connects the pre-trained language model to LLMs, large language models. So this is the connection. So, and starting around 2020, we entered the phase of, I would say, general purpose task solvers. So what we today call large language models. So these models are not, let me say, they are not only solving isolated tasks, but they are capable of tracking real world and open-ended problem across many domains. So this is what we are seeing, and this is where we are living today. Okay. Uh, just to open the parenthesis, so here, this, as I'm saying, this is what we are witnessing, and this is what we are living today. So this is impacting our like daily life. And if I say it's impacting our daily life, so we need to take some control over it, and we need to be very careful while using these like this technology. Even it's really impressive, but we need to like keep like ethics and bias in AI in mind. So this is what you can discover in my upcoming videos. But for now, let's like only think about this evolution. And so this evolution in this context, so I'm also referring here. So all my figures are taken from papers, okay? So and famous papers. So this is why like you can find like very interesting resources that you can go through. Okay. And so this is from where I took mainly the figures. So this survey, and it's a survey on large language models. Okay. So what we have, there is a particular emphasis on OpenAI. So focus is on OpenAI in this paper or in this survey, which allows us to clearly observe the evolution of the GPT family. So we can consider the GPT use case, okay? So starting from GPT-1, we can see, for example, decoder only architecture, okay? And the idea is that we are based on generative pre-training, okay? It's purely through pre-training. So this continues with the GPT-2, and so with GPT-2, what we have is unsupervised multimodal learners scaling the model size, okay? And then this extends to GPT-3, and in GPT-3 here, it introduces, let me say, a more sophisticated architecture component, okay? The architecture is mainly composed of multiple specialized modules. And for example, we have some modules that are capable of code generation. Other modules, for example, are capable of or designed for instruction following, components that support human alignments. And so here we have many components, okay? And maybe others that are significantly there to enhance the comprehension abilities, okay? So building now on this, we have the GPT 4, okay? So GPT-4 mainly expands this architecture with true multi-modal capabilities. And what this allows the model to process different modalities like text, like image, like even more, okay? So together, these milestones like GPT 3.5 in particular and the GPT 4, they are forming today's foundation of the ChatGPT, okay? So GPT-4 also is today we talk about GPT 5 and 5.1 up to date, okay? So, but based on this paper, so it's mainly only GPT-4. So the idea is that this is only shown in the slide, but this variation, and let's say this mainly updates and release in the different versions of GPT are maybe contributing the ChatGPT that we are using daily. Okay. So now what we have there here is like, let me say, the life cycle of a large language model. So at high level, it is built around three major phases. The first phase is the pre-training. So the second, maybe we will see so far, adoption phase and usage phase. But let's now only focus with the first stage, which is the pre-training. Okay, so this phase mainly depends heavily on data. And if we ever wanted to create our own large language model, the first requirement would be massive amount of data. Okay, this also will take you to thinking about the resources, your laptop, or workstation capabilities, hardware, and so on. So, and this is exactly why there is competition between companies, okay? And even I would say disputes about who uses whose data, okay? So data is the true source of strength. And for these models, so in pre-training, we begin with data collection and preparation. So as user or final user of, I would say you take to ChatGPT in DeepSeek, for example, you will feel the difference. This difference mainly could be due to the data. It's possible. It's just a factor. But so the idea is that now, based on data collection step and preparation, what will happen, the model is going to be trained at very large scale. So once the model is trained, we move to the second phase, which is adaption. Okay, so adaption is where the model goes through instruction tuning, alignment tuning, let me say, and efficiency improvements. Like, for example, parameter efficiency, efficient training, and, for example, memory optimization, and so on. Okay, so after that, we enter the final phase, which is the utilization or usage, where we interact with the model through prompting. So whenever you take your phone, you open ChatGPT app or in your laptop and you start writing. So you are prompting the model, okay? And prompting here includes many techniques, okay? So we have, for example, the standard prompting. Standard prompting is I simply ask a question, for example, teach me AI, okay? This is what I will type, teach me AI, okay? So this is standard prompting. There is, I would say, another art or another way, which is prompt engineering. So prompt engineering is when you provide context and guidance. For example, you are going to say, you are an AI assistant. Help with a project on computer vision. The dataset contains, for example, 50K labeled images. Explain the next steps in building a classifier. So here, in this example, you are providing context, you are guiding the LLM, and for sure what you will expect based on the quality of the answer of the model. There is a difference between whether if you are using standard prompting or prompt engineering. So they say that LLMs are not stupid, but the way you deal with them and talk to them is what matters, okay? So it's always in our hands. So now we have two additional concepts that are important to discuss. The first concept is chain of thought reasoning, okay? You would hear about chain of thought reasoning a lot, but to summarize, this means guiding the model to explain its reasoning step by step, okay? So instead of giving a short, direct answer, you can say to the model, explain your reasoning step by step. So here you unlock the model's internal reasoning process, and this is extremely useful for math logic, for planning, for, let me say, problems that require solving in multiple steps. Okay, so the second concept here is besides like chain of thoughts, now we have planning for context tasks. And so when we talk about planning for complex tasks, here modern LLMs can plan a sequence of actions instead of producing a single response. For example, like breaking a big problem into smaller sub stacks, let's say. This is just an example. Um, so another example could be maybe generating or designing a multiple step project in addition to like generating an ordered workflow. Okay, so this makes LLMs very useful, not only for text generation, by the way, but also for project planning, for decision making, and for multi-stage reasoning. So together, all these capabilities prompting the chain of thoughts, like planning for complex tasks or structured planning, define how we interact with the large language model. Okay. The question now is how large language models work in practice. Okay, so this is the first step. The first step is mainly tokenizer. And this is where we convert text into numbers, okay? We deal with the numbers, scalars. So when you prompt a model like GPT, you mainly type natural language, you write your text. But the model, as I mentioned before, like can only work with numeric vectors. So the first step that we need to encode the text that you like write, and this encoding step is critical, like we discussed. So there are mainly different ways to tokenize, and the choice of tokenizer can influence absolutely like the final output and even the behavior of your model. So this is like just a simple example and of tokenizer. So what we have here, this is our like prompt. The question is written in natural language. So we have what is a tokenizer, okay? And now the idea is that uh, tokenizer now is going to convert this sentence into sequence of tokens, okay? And like, so instead around like 20 characters in this sentence, okay, we might end up with only, let's say, 6 tokens, okay? So this is the idea. And these tokens are what we get mainly passed to the model architecture. Okay, so the concept is simple. Here I made this a separate video to give you the overall idea, but if you really will understand the foundations, you come back to the previous 2 videos. Transformers part 1 and part 2 has all the details about how to tokenize, what we use, the RNNs, the LSTMs, and the architecture itself, and so on. Okay, so mainly these tokens are what we need, at least at this step. Okay, so the next step is predicting the output tokens. So in a decoder-only architecture, the model uses what we call autoregressive decoding. And autoregressive decoding means it predicts the next token one step at a time, okay? Conditioned on the previous token each time, okay? So this is mainly the prediction, okay? And this is how it works. So this is the like how um, autoregressive decoding works, okay? So we have here like step 1, time step 1, time step 2, and time step 3. So each time, first, like we are dealing with decoder only architecture, okay? The dog we have, then the dog like that here is decoder only architecture. Now here we're moving further. So each time step we are adding one new token, okay? So down and so on, the third time step. So it's there is kind of auto regression, okay? So now during the training, what we do is we go or we have the step of selection, and the selection process is where we discuss the probability distribution over the possible next tokens, okay? So here the model assigns, let's say, probabilities to every candidate token. Like you have, like for this token, there will be a probability, this token, there is a probability. For each like token, there will be a probability like we've seen so far. And so what we will obtain at the end from these all probabilities is a distribution, okay? And so by forming this distribution now, like during the training, what we will do is like we are going to measure how good these predictions are, okay? And this is mainly using language model loss. And so here is the formula of language model loss over the full text corpus, okay? So typically it is the sum of log conditional probabilities parameterized by the model weights, okay? So in summary now, tokenize the input, the first step. Next, we predict output tokens, and this is using the autoregressive decoding. Next, we train our model by optimizing the probability based on this kind of loss, okay, the language model loss. And so like this, we can, of course, maybe dive deeper into each of these steps, but this is the high level pipeline, okay? So the applications of LLMs today are extremely broad, let me say. One major use case is summarization. So whenever you ask a model to make it shorter or summarize this paragraph, it performs very good or high quality text, let me say, compression, while you feel that it keeps or it preserves the meaning. So this is the idea of summarization. Another now important application is maybe the creative ideation. Creative ideation, I mean like generating new concepts when you are brainstorming with like ChatGPT, for example. And it helps you maybe with brainstorming, with supporting innovation and expanding probably like possibilities beyond what a human might like initially think of. So we also have a very important application, which is a code generation. So which has become, let me say, one of the most impactful use of LLMs. So in fact, our for my own research work, I have some experience with AI with software engineering. And so one of the works we did is the intersection of LLMs and software engineering. So what we did is mainly we used LLMs for tasks like code refactoring, okay, means changes that happen within the code, okay? And like, for example, what was really great in that research is that it shows that LLMs are actually outperforming humans, yeah, because if in the developers area. So the task that we give to ChatGPT and it did the code refactoring, let's say, faster than developers that may take 2 weeks to do that. So it's extremely uncomparable, in terms of time and also the accomplishments of the model, okay, in just a few hours. So just amazing. So for the quality is still strong like quality, even as compared by developers who also can like commit some mistakes. But so overall, like let me say that LLMs have become powerful tools, or not only in writing or for creativity, but also in technical domains like software engineering and so on. Okay. This brings us, let me say now, to the future of LLMs. So we started with text. This is our starting point. Then what we did, we moved it to images, to audio, now video, which is amazing. And like the next frontier is introducing even more modalities, probably with AR, VR, and so on. So just I'm thinking. But for example, you can think even about code as an input modality, which is great. So a regular user can simply upload, for example, a file without worrying about anything and just to upload. Sometimes I don't know if there are images, there is text only, quality, colors, and so on. Just to upload and that's it. So this is mainly for users, so they don't worry about anything else. But we as architects, or for example as researchers, must think deeply about like how that code mainly is represented, that figure, how it is like embedded, that text, how it is mainly encoded, and so on. So which embedding are we going to use? How are we mainly going to choose the method for an accurate or good tokenization? Is tokenization having an impact on the output of the model? All these are RQs, I mean research questions, okay? So what representation will allow the model to understand its structure, or like what will allow the model to give us the best results? So this question become central as like LLMs expand beyond nature, like natural language. So the future now is, it's not about feeding more modalities into the model. It's also enabling the model to produce richer outputs. Imagine like a language model generating an entire video from a text description. So this is no longer science fiction, by the way. So with generative models, GANs or diffusion models, and now video generation models also, we can already create images and even videos directly from prompts. So you can give a photo and a piece of text, and the model can animate it or transform it. So this is becoming my favorite thing when I'm teaching online, and especially asynchronously. So I love using that avatar of mine, I call it my AI generated uh, version. I love first activity with the students that I do. I generate they don't meet me first, they meet my AI generated version. And I love that. I ask also my students to create their AI generated version to introduce themselves. And so it's amazing. So this is really great activity that I love it, by the way. And thanks to LLMs. Okay. And so the future of LLMs is mainly, I can say, is multimodality, okay, multimodal LLMs, which means not just text to text or text to image, text to video, code to text, interesting. We can think even code to code, why not? So based on our current trajectory, these capabilities will almost like, and I would say certainly like, go far beyond what we are witnessing today. So thank you so much. And I tried to summarize things in this last video. I wish you love it. Okay. Thanks for watching. So if you have any questions, never hesitate to ask again, to send me like messages, emails, or like whatever.